Hello, my friends. Hello, my friend. Where are you, my friend? Good morning. Welcome to your Friday Math Minute. We are going to jump right in to double distribution. Except no, we're not going to jump right into double distribution because there's something I want to show you first. And you can see it here. Every once in a while, this comes up. Article on CNN just a few days ago, comes out Tuesday. Parents' biggest frustration with distance learning. You want to guess what it is? Teaching math, right? How are we supposed to teach our kid math? And it's bad enough trying to teach our kid math. How are we supposed to teach our kid the new way to do math, right? And so this comes up every once in a while. I actually saved a few months ago. This thing popped up on social media. A parent was saying, oh, so this is like what teacher is showing in class, which haha, whatever, let the kid do whatever they want as long as I, the parent, don't have to teach them. But as soon as I, the parent, have to teach them, this is what we won't do, right? We're going to go back and make sure that we are doing the stacking algorithm that we were taught in 4th grade, and we're going to, by God, make sure that our son or daughter knows how to do the stacking algorithm. So there's nothing wrong with the stacking algorithm. Stacking algorithm is fantastic, but do you wonder as a parent maybe why math teachers like myself are making your children draw these silly boxes? Maybe you don't wonder. Maybe it just annoys you. But I'm going to show you anyway where these silly boxes are coming from. So let's consider, this is actually, really honestly, this is an amazing example of precisely why we do the box thing. But let me come back to it first. Let me talk about the box thing. So let's say that I wanted to multiply, and all of this, by the way, is actually purposed to eventually get to other kinds of math tricks. So, I showed you this one the other day. This is one of my favorite ones in the world. 103 times 105. Most people, of course, would presume they can't do something like 3-digit number multiplication in their head, and yet it's very simple to say that this is 10,815. So what I'm about to show you is, in fact, related to how I so quickly know that that's going to be 10,815. But we're not going to jump there just yet. We have to kind of establish why or what double distribution even really is and why it works. So consider an example, and this is the example you'd see pretty much any teacher start with. It's all over the internet. Let's say you wanted to do 23 times 12, right? If you learned math, like I did in the 80s, you would have learned what's called the stacking algorithm, where once we get our times table, the tens multiplied out, memorized, we know all the single-digit multiplications, and so we just multiply a bunch of single-digit multiplications and then eventually add stuff together. So like here, you would start with 2 times 3, which of course is 6, and so that's what we write down here. And then you move over, you do 2 times 2 is 4. And you might have a vague sense of why we do it in this particular order. Like perhaps you notice, 23 times 2 is 46, right? But also one of the problems with an algorithm is that we end up just kind of memorizing steps and not really understanding why they work. But that's also one of the benefits of an algorithm, is as long as we just do the steps in the same order every time, we're going to get the right answer. But again, there is actually a reason. It is related to the fact that 2 times 23 is 46. And then okay, now we're supposed to move over. But again, when we move over, for some reason, we put a 0 here, or maybe a blank, or a placeholder. And then we do the 1 times the 3 is 3. 1 times the 2, of course, is 2. And finally, to actually finish this up, we add these two things together. And again, it's not super clear if you actually think about, well, wait, why do we do addition to perform multiplication? But it's in the algorithm, right? So we do it, and we get 276. And that's that. That is, in fact, the correct answer. 23 times 12 is 276. What your kid's math teacher is going to have them do, at least for a little while, we still teach the stacking algorithm. It just comes later. What your teacher's kid is going to tell them to do is use something called an area model for multiplication. So here's how an area model works. Imagine that this is literally a rectangle, and we're going to find some different areas, right? Like, imagine I had a 2x4 rectangle. What would its area be? Well, you can actually see we can split it up into 2 blocks by 4 blocks, and its area is 8. Now, of course, we don't normally split it up into the blocks. We usually just say, oh, 2 times 4 is 8. So when we're coming up with area, we naturally multiply. We're going to do the same thing in this box up here. We're going to take these numbers, 23 and 12, and we're going to split them up into their tens portion and their units portion. In other words, we want to think of the numbers as actual numbers. 23 is the sum of 20 and 3. 12 is the sum of 10 and 2. We're going to literally find the areas of these different boxes, but you'll notice because of the way we've broken the number up, and this is where the distribution comes in. If you watched Wednesday's math video, you should start to see, oh, we're splitting the 23 into a 20 and a 3, and we're going to do some kind of distribution. Because of the way we've chosen to split the numbers up, all our multiplications right now are really easy. 10 times 20 is 200. 10 times 3 is 30. 20 times 2, so this box here, 20 times 2 is 40. If I can get that error to go away. And then this box here, 3 times 2 is 6. This would have an area of 6. And it just so happens that when we add up the total area, 200 plus 30 plus 40 plus 6, oh my goodness, it makes the self-same 276. So this area model for multiplication is helping us understand why in the standard algorithm we eventually add things and what's going on there at all. It helps us understand where these numbers are coming from. You'll notice these numbers are actually in our standard algorithm. 230 is 230. 40 and 6 is 46. But now we have a sense of where those numbers are coming from and what they represent. They do represent different multiplications, but also if we think of it with a model, this area model, they literally represent the area of rectangles. So let's come back to this pandemic example. This was, again, from something that went around social media back in, what's it called, the spring, the before times. Well, actually not the before times, the just after times. We've got 312 and we're multiplying by 23. Again, standard algorithm down here, you would just do 312 times 23, and you would do all the various steps, right? So 2 times 3 is 6. 3 times 1 is 3. 3 times 3 is 9, and so on. And then you switch gears and you do 2 times 2 is 4. 2 times 1 is 2. 2 times 3 is 6. And finally, of course, you add it all together. And so that's where we're getting 7,001. There's a carry there you can see. 7,176. Of course, the standard algorithm works. Nobody thinks, oh, there's something wrong with the standard algorithm. But it doesn't really help us make sense of where this is coming from. Whereas with 312 times 23, if I literally split the number up into 300, 10 and 2 for 312, 20 and 3 for 23, I can see where all these individual numbers come from. 2 times 20 is where we get the 40 from, right? So that's 40. 2 times 3 is where we get the 6 from. 10 times 20 is what gives us the 200. 10 times 3 is what gets us the 30. 300 times 20, 6,000. 300 times 3, 900. And then over here, we just add all of this together. 6,000, 900, 200, 30, 40, and 6. And again, that's where we end up getting 7,176. For this, it's like, okay, so I understand the area model, but once I kind of get good at the area model, isn't it better just to go to the standard algorithm? And the answer in some cases is definitely going to be yes, but not in every case. So I'm going to have to finish with this because I don't even know how I'm going to end up cutting this down. Let's go back to that example I was showing you earlier of 103 times 105. And again, I mathematically know that this is 10,815. What is it that I'm doing in my head? You can tell some interesting things end up happening. 100 times 100, well, that's going to be 10,000 if we just write down all those zeros, and the 1 times 1 is 1, right? And then 3 times 100, that's going to be 300. 100 times 5, this box down here, is going to be 500. And of course, 5 times 3 is 15. Now, what ends up being nice about that particular set of numbers is you can probably tell pretty easily, oh, when we add everything together, everything kind of has a place, right? Like the 15 is the only thing that could possibly go in these last two digits. The 3 and the 5 is the only thing that could possibly go in this middle digit. And then, of course, we're just going to begin with our 10 from the 10,000, and so that's what ends up going at the front, 10,815. And now what we would want to do is generalize this. Now I would want to take a set of several different numbers slightly above 100 and just practice coming up with different results. But we'll have to do that next time. So I'll write the rest of these out. We'll practice. I'll show you how it works. But there it is. That is double distribution, the area model for multiplication. Hopefully that's helpful to you. Hopefully that makes a little bit more sense of why your teacher is randomly torturing you and your children with this new model for multiplication. If not, though, well, we're going to keep doing it till morale improves.